the International Electrotechnical Commission, or IEC, website at IEC.ch/wellplug provides information on plugs and sockets used around the world. The World Standards website at World Standards. EU/electricity/plug voltage by country/ offers details on voltage and plug types by country. Electrical technology. OG/2016/5/electrical power standards countries and their electrical standards. HTML provides a description of electrical power standards for various countries. Voltage ranges vary significantly across the globe. In the United States, the standard voltage is typically between 100 and 120 volts. In Europe, Australia, and much of Asia, the voltage range is generally between 220 and 240 volts. Electrical frequency also differs by region. Most of Europe and parts of Asia operate at 50 Hz, while the United States and Canada use 60 Hz. When teaching electrical installations to foreign students, safety is paramount. Students should be thoroughly briefed on the potential hazards associated with different voltages and frequencies. Always ensure that the equipment used in a lab is appropriate for the voltage and frequency being utilized. All training materials must be adapted to reflect the different standards and practices prevalent in various countries. Concerning third world countries, their electrical infrastructure can be unreliable. This can result in frequent power outages and fluctuations in voltage. Also, electrical installations in these regions may not consistently meet established safety standards, heightening the risk of electrical hazards. The students from these countries might not have extensive experience with modern electrical systems. Industrialized countries generally have more reliable electrical infrastructure that aligns with high safety standards. Students from these nations might already have a solid understanding of modern electrical installations. It is important to verify that each country has its own unique electrical standards and practices. You may consult with the local utility company to ascertain the specific voltage and frequency for the area where the teaching will take place. When practical, encourage students to bring their own electrical equipment. Doing so can minimize any potential compatibility problems. Ensure that there is adequate time for students to adapt to the distinctions in voltage and frequency. It is crucial to emphasize the significance of using appropriate adapters and converters when working with different voltage systems. Explain how these devices work and their limitations. Discuss the potential dangers of using incorrect adapters or converters. Educate students on identifying the voltage and frequency requirements of electrical equipment. This knowledge is crucial for safe and effective installations. Provide practical exercises that involve measuring voltage and frequency using appropriate testing equipment. This will give the students hands-on experience and reinforce their understanding. Demonstrate how to properly ground electrical systems in accordance with the relevant standards. Explain the importance of grounding for safety and preventing electrical shock. Cover the various types of wiring methods used in different countries. Highlight the differences in wire colors, insulation, and conduit systems. Teach students how to read and interpret electrical diagrams and schematics from different regions. This will enable them to understand and troubleshoot electrical systems effectively. Discuss the different types of electrical protection devices used in various countries. Include circuit breakers, fuses, and residual current devices, or RCDs. Emphasize the importance of selecting the correct protection devices for the specific application and voltage level. Explain the role of national and international electrical codes and standards. Familiarize students with resources such as the National Electrical Code, or NEC, and the IEC standards. Show them how to access and interpret these codes. Cover the procedures for safely disconnecting and isolating electrical circuits. Emphasize the importance of lockout-tagout procedures to prevent accidental energization. Discuss the potential hazards associated with working on live electrical circuits. Emphasize the importance of de-energizing circuits whenever possible. Explain how to use personal protective equipment, or PPE, such as gloves, safety glasses, and insulated tools. Emphasize the importance of using the correct PPE for the specific task and voltage level. Teach students how to troubleshoot common electrical problems such as short circuits, open circuits, and ground faults. Provide them with the tools and techniques needed to diagnose and repair these problems. Demonstrate how to use various types of electrical testing equipment such as multimeters, clamp meters, and insulation testers. Explain how to interpret the readings and use them to diagnose electrical problems. Discuss the different types of electrical components used in installations such as resistors, capacitors, inductors, and transformers. Explain how these components work and how they are used in different circuits. Cover the principles of electrical power distribution from the power plant to the end user. Explain how voltage is stepped up and down using transformers. Discuss the different types of power distribution systems, such as single-phase and three-phase systems. Teach students how to calculate voltage drop in electrical circuits. Explain how to select the correct wire size to minimize voltage drop and ensure adequate power delivery. Discuss the importance of power quality and the factors that can affect it, such as harmonics, voltage sags, and voltage swells. Explain how to mitigate these problems using power quality equipment. Cover the principles of energy efficiency and how to design electrical installations that minimize energy consumption. Discuss the use of energy-efficient lighting, motors, and appliances. Explain how to conduct an energy audit of an existing electrical installation and identify opportunities for energy savings. Discuss the different types of renewable energy sources, such as solar, wind, and hydro. Explain how to integrate these sources into electrical installations. Cover the principles of electrical safety and how to prevent electrical accidents. Emphasize the importance of following safe work practices and using appropriate PPE. Discuss the legal and ethical responsibilities of electricians and electrical engineers. Explain the importance of complying with all applicable codes and standards. Encourage students to continue their education and stay up to date on the latest electrical technologies and safety practices. Provide them with resources for further learning, such as professional organizations, trade publications, and online courses. Specifically, when teaching about grounding systems, explain the differences between equipment grounding and system grounding. System grounding refers to connecting the neutral point of a power source to earth, while equipment grounding ensures that conductive parts of equipment are connected to ground to provide a low impedance path for fault currents. In the United States, the National Electrical Code, or NEC, specifies grounding requirements in Article 250. It details the methods for grounding and bonding electrical systems to ensure safety. Different countries may have their own specific regulations for grounding, so it is important to research and understand the local requirements. In the United States, the 120/240 volt single-phase system is commonly used for residential applications. This system uses a center-tap transformer to provide two 120-volt supplies that are 180 degrees out of phase with each other. The 240 volts is obtained by connecting to both ungrounded conductors. The 208-volt three-phase system is commonly used in commercial buildings. This system is derived from a three-phase transformer with a Y connection, where the voltage between any two phases is 208 volts. The 480-volt three-phase system is typically used in industrial facilities for powering large equipment. This system also uses a three-phase transformer with a Y or delta connection. The voltage between any two phases is 480 volts. The 277-volt system is also common in commercial and industrial settings, and it is mainly used for lighting. This voltage is derived from a 480-volt Y-connected system, where the voltage from each phase to neutral is 277 volts. In addition to voltage, frequency plays a crucial role in electrical systems. As previously mentioned, the United States uses a frequency of 60 Hz, while many other countries use 50 Hz. Frequency affects the operation of electrical equipment, particularly motors and transformers. Operating equipment at the wrong frequency can cause overheating, reduce performance, and even damage. Therefore, it is essential to ensure that equipment is designed and rated for the correct frequency. When teaching about branch circuits, it is important to cover the different types of circuits and their applications. Branch circuits are the circuits that extend from the final overcurrent device to the outlets, lighting fixtures, and equipment. In the United States, the NEC specifies the requirements for branch circuits in Article 210. Branch circuits are classified based on their ampacity, which is the maximum current that the circuit can safely carry. Common branch circuit ratings include 15 amps, 20 amps, 30 amps, and 50 amps. 15-amp circuits are typically used for general lighting and receptacles in residential buildings. The NEC specifies that 14 American wire gauge, or AUG, copper conductors can be used for 15-amp circuits, provided they are protected by a 15-amp overcurrent device. 20-amp circuits are commonly used for small appliances, such as kitchen appliances and laundry equipment. The NEC specifies that 12 AWG copper conductors can be used for 20-amp circuits, provided they are protected by a 20-amp overcurrent device. 30-amp circuits are often used for electric dryers, water heaters, and air conditioners. The NEC specifies that 10 AWG copper conductors can be used for 30-amp circuits, provided they are protected by a 30-amp overcurrent device. 50-amp circuits are typically used for electric ranges and large air conditioning units. The NEC specifies that 6 AWG copper conductors can be used for 50-amp circuits, provided they are protected by a 50-amp overcurrent device. Overcurrent protection is essential for protecting electrical circuits and equipment from damage due to excessive current. Overcurrent devices include circuit breakers and fuses. Circuit breakers are electromechanical devices that automatically interrupt the flow of current when an overcurrent condition occurs. They can be reset manually or automatically after the fault is cleared. Fuses are one-time devices that interrupt the flow of current when an overcurrent condition occurs. They must be replaced after they blow. The NEC specifies the requirements for overcurrent protection in Article 240. The overcurrent device must be sized to protect the conductors and equipment in the circuit. The overcurrent device rating should not exceed the ampacity of the conductors it protects. When selecting conductors for electrical installations, it is important to consider several factors, including the ampacity of the conductor, the temperature rating of the insulation, and the environmental conditions. The NEC specifies the requirements for conductor selection in Article 310. The ampacity of a conductor is the maximum current that it can safely carry without exceeding its temperature rating. The ampacity of a conductor depends on its size, material, insulation type, and installation method. The temperature rating of the insulation is the maximum temperature that the conductor can withstand without degrading. Common insulation temperature ratings include 60 degrees Celsius, 75 degrees Celsius, and 90 degrees Celsius. The environmental conditions can affect the ampacity of a conductor. For example, conductors installed in hot environments or in raceways with multiple conductors may have their ampacity derated. When installing conductors in raceways, it is important to follow the NEC guidelines for fill capacity. The fill capacity is the maximum percentage of the raceway cross-sectional area that can be occupied by conductors. The NEC specifies the fill capacity for different types of raceways in Chapter 9. Proper grounding and bonding are essential for electrical safety. Grounding provides a path for fault current to flow back to the source, allowing the overcurrent device to trip and de-energize the circuit. Bonding ensures that all conductive parts of the electrical system are electrically connected, minimizing the potential for voltage differences and shock hazards. The NEC specifies the requirements for grounding and bonding in Article 250. The grounding electrode system consists of one or more grounding electrodes that are connected to the earth. Common grounding electrodes include ground rods, metal water pipes, and concrete encased electrodes, or U for grounds. The grounding electrode conductor connects the grounding electrode system to the electrical system. The equipment grounding conductor, or EC, provides a path for fault current to flow back to the source from non-current carrying metal parts of equipment. The bonding jumpers connect different metal parts of the electrical system together to ensure electrical continuity. Surge protection devices, or SPDs, protect electrical equipment from voltage surges caused by lightning strikes, utility switching, and other transient events. SPD divert the surge current to ground, preventing it from damaging sensitive electronic equipment. The NEC specifies the requirements for surge protection in Article 285. SPD should be installed at the service entrance and at downstream locations to protect critical equipment. Electrical safety is of paramount importance when working with electrical systems. Always follow safe work practices and use appropriate personal protective equipment, or PPE. Energize circuits before working on them whenever possible. Use insulated tools and equipment to prevent electrical shock. Lockout-tagout procedures should be followed to ensure that circuits are not accidentally energized while being worked on. Regular inspections and maintenance of electrical systems are essential for preventing electrical hazards. Inspect wiring, connections, and equipment for signs of damage or deterioration. Test ground fault circuit interrupters, or GFCIs, and arc fault circuit interrupters, RFCIs, regularly to ensure that they are functioning properly. Repair or replace any defective components promptly. Understanding and adhering to the National Electrical Code, or NEC, is crucial for ensuring electrical safety. The NEC is a comprehensive set of standards for electrical installations that is updated every 3 years. It covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. The NEC is adopted by many jurisdictions in the United States and is used as a basis for electrical codes in other countries. In addition to the NEC, there are other standards and regulations that may apply to electrical installations, such as those issued by the Occupational Safety and Health Administration, or OSHA, and the American National Standards Institute, or ANSI. It is important to be familiar with all applicable codes and standards and to follow them carefully. When teaching electrical installations, it is important to provide students with hands-on training and practical experience. This can be accomplished through laboratory exercises, field trips, and internships. Students should be given the opportunity to work on real electrical systems under the supervision of qualified instructors. They should also be taught how to use electrical testing equipment and how to troubleshoot electrical problems. It is also important to teach students about the ethical responsibilities of electricians and electrical engineers. They should be taught to always put safety first and to never compromise on quality. They should also be taught to respect the environment and to conserve energy. By providing students with a comprehensive education in electrical installations, they will be well prepared for successful careers in the electrical industry. The ability to navigate diverse electrical standards and practices will become a valuable asset in an increasingly interconnected world. As technology advances, new electrical technologies and practices will emerge. Therefore, continuous learning and professional development are essential for electricians and electrical engineers. They should stay up to date on the latest codes, standards, and technologies by attending conferences, reading trade publications, and taking continuing education courses. With a commitment to safety, quality, and continuous learning, electricians and electrical engineers can make a significant contribution to society by providing safe, reliable, and efficient electrical systems.